All right, let's go ahead and get started. My name is Greg Schmidt. I'm director of the Solar System Exploration Research Virtual Institute based at NASA's Ames Research Center, about an hour drive south of here, or maybe more like 3 hours in rush hour. And we are just so honored to be spending the 50th anniversary of the Apollo 11 landing on board the ship that picked up the crew. What an amazing honor that it is. I want to start off by thanking Captain McCarran and Laura Fees for their kindness and working with us for several months to make all of this happen. So, Captain McCarran. So we have a special program for you today, and we're going to start off. I will make an introduction in just a second. We're going to start off by a panel on lunar geology, past, present, and future. Then we have a special surprise event that I'll tell you about when this panel is over. That's going to be just a few minutes. And then we're very privileged to have three leaders from NASA to be talking about our future plans to go to the moon. We figured it was appropriate. We're looking back 50 years. Well, let's look ahead as well. NASA has some pretty exciting plans. So with that, I'm honored to introduce Dr. Jacob Bleacher, who is the Chief Scientist for the Human Exploration and Operations Mission Directorate at NASA headquarters. So, Jake.
So this is quite an event, I'll say. I'm very excited to be here. I think all of our panelists, myself, many of you in the audience and maybe listening online have spent a large part of the last week, several weeks, telling stories about Apollo, listening to stories about Apollo as we head into this anniversary. I think it's a fair claim to state that the Apollo missions to the moon are among the most amazing stories ever told. But they're not just a story of a launch or a landing, it's also a story of a return to Earth, a splashdown in the Pacific Ocean, and this ship rescuing and bringing back our crew members and our rocks, the samples that they brought along. It's also a story of individuals, of a nation, of humankind. And I hope that this panel will demonstrate that it's a story that's not actually done yet. It's a story that we're going to continue to tell. It maybe started with Apollo, but we're going to keep going. And so that's where we are today. And so I'd like to introduce our panel to you. Down on the left is Ariel Deutsch. She's a PhD candidate at Brown University. She's a NASA graduate fellow at the Goddard Space Flight Center. She studies processes related to volatiles, volcanism, impact cratering on the moon, and she represents the next generation of researchers who will support the efforts to place our astronauts on the moon by 2024. Beside her is Jennifer Heldman. She's a research scientist for NASA's Ames Research Center, has served as a director for Survey's Field Investigations to enable solar system science and exploration, or FINESS. She's also now leading a new Survey team, Resource Exploration and Science of our Cosmic Environment, or RESOURCE. Jen has been involved in bridging research and exploration goals between the moon and Mars, including a focus on understanding the role that volatiles play as a resource for astronauts as they explore our solar system. Beside Jen is David Kring, and he serves as a principal scientist at the Lunar and Planetary Institute in Houston. He also serves as the director for Survey's Center for Lunar Science and Exploration. David studies processes related to impact crater development and evolution on the Earth, Moon, and planets. In addition to his research focus, he's led many field training exercises to help develop the next generation of planetary scientists, as well as to help train our astronauts. And he applies his research to help develop the human exploration architectures that will help return us to the moon. Beside him is Jack Schmidt. He's a research scientist, he's a geologist, he served as a U.S. Senator, He's also a crew member of Apollo 17, and he walked on the surface of the moon. But he wasn't only an Apollo 17 crew member. During Apollo 11 EVA, he served as a Capcom support, thereby ensuring that science had a voice during this momentous occasion. His role with lunar research did not end in Apollo. Jack has served as a powerful advocate for lunar science and human exploration. He also serves as a mentor to many of us here, and the work that he does will help us also return humans to the moon. Now I'll go ahead and get this started off, but really we want to hear the questions that the crowd has. So hopefully this will be engaging, we'd like to hear again from our panel about how we're going to continue to tell this story about exploring the moon and beyond. So just to get started, I'd like to go ahead and ask the panel members to just give a brief story or favorite memory, Apollo 11, and what it really means to them to be in the positions they are today. So Ariel, maybe we'll start with you.
I wish I had a favorite Apollo memory to share. But I think that the Apollo program is the true epitome of exploration, and it's that discovery aspect that really inspired me to become part of this community. And I think it's really clear this week that the impact that the Apollo program had was very powerful and inspirational, emotional, and it was felt worldwide. But I didn't experience it, and I don't think a lot of people in this room had the opportunity to experience it. And you asked us to think a little bit about one of our favorite images of Apollo, and I kind of went back and forth with all of the images of astronauts on the moon, and you're looking out on this vast landscape, and those always get me, but one of my favorite images is actually back on Earth in Mission Control, where people are really looking at the first time that man stepped on another planet, and the inspiration, the excitement in those faces is really, I think, cool, and that's something that I want to be a part of. And the other thing about those faces is that they're all very young, and we heard a little bit about that just before. The people involved in the Apollo mission were in their 20s and in their early 30s, and so as a young person entering the field, I think that's really inspirational, and can't wait to be part of continuing that legacy.
So, right, similar to Ariel, I was not born yet during Apollo, even when Apollo landed. But I feel that I owe most of my career to what Apollo accomplished, because that's, when I thought of Jake's question, he asked us earlier, it was inspiration. Because now we know when people like Jack, which by the way, if you ever work at NASA, which I hope many of you do, because there are many young people in the audience, I feel that this is one of the occupational hazards. Or you can go to the tour. 3:15 if you'd like to leave. But please stay. But it's an occupational hazard of working at NASA because astronauts are the coolest people on the planet, well, and off. And then on occasion, if you work for NASA, you end up on a panel with astronauts. And then you end up in a panel with an Apollo astronaut, and that's like the top of the top. So I'm very honored to even be here today. But it's the inspiration, because as Jake had mentioned before, what I've worked towards, and many other people at NASA and people that work with NASA, is having a sustained human presence out in space. And so just by virtue of the Apollo program happening, we know that that is possible, that we can do that. We can send people to other planetary surfaces. And so it becomes something that's tangible that we know we can do. And so the work that I've been doing, and many, many others in this room and elsewhere, is looking how can we make this sustainable. So I've focused a lot of my research on looking at water and ices and volatiles in the solar system with an eye towards both the science and also towards using that water as a resource. In situ resource utilization, living off the land, so to speak. When you go to explore, you use the resources that are there. And water is a very valuable resource. You know, you can drink it and you can brush your teeth, but water is H2O, so you can break it apart, and that's hydrogen and oxygen, and that's how you make fuel or propellants. And so that gives you a lot of capabilities to have a sustained presence. So that's one of the very exciting things. And then just to emphasize what Ariel said, you know, for the early career folks, and even in high school and middle school, you're the ones that will be making this happen. You will be the ones that will be sending people out for longer periods of time. So we're trying to help you and lay the groundwork so that you can do that. And I just have one quick story, because I feel like the future is happening now, and the future that we want to see is happening now. Because a couple weeks ago, I said to my 8-year-old daughter, I said, you know, NASA's going to send a girl to the South Pole of the moon in 2024. And she just looked at me like I was really dumb. And she said, well, NASA's already sent people to the moon, so they've already sent girls, so what's the big deal? And I was dumbfounded, and I didn't even know how to respond. And so I didn't. And she just went back to doing whatever she was doing. And then I thought about it, though, and I thought, this is fantastic, because she's growing up in a world where she doesn't see the limitations. She doesn't see that, you know, girls can do this or boys can do this or any gender identity. It doesn't matter. If you're a person and you want to do something, then you go and do it. And so I feel like we are starting to see that become a reality, and so I think that's also a bright point for the future of human exploration.
If I had to choose a word, it would be, as Jen said, inspiration. When Apollo 11 happened, and I am old enough to have seen it, it was a treasured moment in my life, as I think it was for most people in my generation. The minute you saw the astronauts land on the surface and return safely to Earth, anything was possible. I mean, literally anything was possible. For me, what I wanted to make possible is be a planetary scientist. And I say that, but those words, by the way, didn't even exist at that time. There was no planetary science department. And so you did have to figure out, you had to navigate a way into the profession. But one of the things that I remember is having a tremendous number of mentors, and that's something I'll never forget. For me, it was Basu at Indiana, Gordon McKay and David McKay at JSC, Ursula Marvin and John Wood at Harvard, where I went to school, and other people in the field like Jack. So Jack won't remember this, but when I got my PhD from Harvard and got my first...
Are you saying that I'm too old to remember things?
No, it's just because you're one of these people who does so many things for so many people, you can't possibly keep track of all of them. So I get my first posting at the University of Arizona, and I'm sitting in my office one day and somebody walks in with my mail, and there's a letter from Jack Schmidt. And he says, I understand that you have a new post at University of Arizona. And he sent me a reprint about some Apollo finding that you had. I have to admit, I don't recall, but I still have it. And he had some remarks on that cover. It's like, there's all these people, as a young person trying to gain a foothold in the profession, that were a positive influence, right? So I'm now at the end of my career, or getting close to the end of my career, and I try to do the same thing. Don't laugh, Penny.
She was laughing at me because I looked askance.
Yeah. You're a special person, Jack. I won't have your energy at your age. But so I'm absolutely thrilled that I've had an opportunity, as Jake said, to train astronauts and train graduate students, undergraduates, high school students, undergraduate students, graduate students, and postdocs. And I probably have another 10, 15, maybe 20 years to do that. And what I would like to give them is the one thing I have to say my mentors failed to give me, and that was an opportunity to be part of a lunar mission. I really hope we pull this 2024 thing off. I know I am working day and night. It's so important because I want to go back to that word that I started with. Apollo 11 was inspiration. It inspired everybody in this country. Anybody could do anything. And I'd like to give the new generation that very same feeling.
hope somebody will ask me later about why did we fly the experiments we flew on Apollo 11. But I want to talk a little bit about the origin of the selection, the landing site selection for Apollo 11. It goes all the way back to Apollo 8. As many of you are aware, we had, for the early Apollo missions, we had sites identified across the equatorial belt of the moon that were spaced with about a 2-day delay in the launch window from Florida. And Apollo 8 was targeted to the easternmost of these sites, which had been characterized to the best of our ability using the photography available at the time. That included some pretty good lunar orbiter photography. After Apollo 8, the crew came back, and particularly Bill Anders, and he said, you know, we looked very carefully. We had a 10-power monocular on board. Looked very carefully from 60 nautical miles at the easternmost landing site to which we were targeted, and it looked pretty good based on what we could see. And this triggered in my mind, said, well, now let's see, we've got 2 days between landing sites. Why don't we get the same good feeling about, if we can, about the next 2 landing sites? So I went to Tom Stafford and said, Tom, is it okay if I work on delaying your launch day, turns out by 1 day, so that we can, so that you all can look at those next 2 landing sites, because they were going to be in orbit long enough to see 2 more landing sites. What did that mean? That meant that if you targeted Apollo 11 to the easternmost site, then if there was a reason why you didn't launch, you had 2 more choices that we had really looked at, even though it was from a fairly high altitude. And he said, go ahead, see what you can do. And so I began to carry out one of my little lobbying campaigns, which you could do in those days. Decisions were made very quickly. And once I had all the view graphs, everybody remember what a view graph is? There you go. Had all the view graphs prepared. The first major manager that I went to was the now unfortunately late Chris Kraft. And Chris had a little meeting in his office with some of his senior managers, and I made the presentation, and Chris was looking very skeptical, and then suddenly the lead recovery officer, Jerry Hammock, jumped out of his chair and he said, you mean you can do all of that and we get a daylight landing too? People forget Apollo 8 landed in the dark, and that was not good. Jerry did not like to have his splashdowns in the dark. And so that sort of persuaded Chris that maybe that was something worth thinking about, and we gradually moved it up. Gradually meant the next day we made our briefing to George Lowe, who was the Apollo spacecraft program manager, and George was also very skeptical, because what it meant was that they couldn't use, if they delayed the launch of Apollo 10 by a day, they couldn't use what they call the data pack for the mission that they had already prepared for Apollo 8, and they would just need to modify a little bit. And so he was quite skeptical because of that, but it turned out that the Apollo program manager, Sam Phillips, was General Sam Phillips was in the office that night. By the way, this briefing took place about 10 o'clock at night, and we worked till 10 o'clock at night in those days. Sam was there, and he didn't say a word, but the next morning, Tom Stafford called me and said, Jack, you sold it. We're going to launch on the 17th of May instead of the 16th, or maybe it was the 18th instead of the 17th. And that is what finally determined the Apollo 11 landing site, because by God, they weren't going to redo the data pack again. And so they used the Apollo 10 data pack, and that was Tranquility Base. So now you know why we landed at Tranquility Base. I look forward to your questions.
Okay, I'm going to start out with one question, and then we'll have about 30 minutes for unless we talk really long, then maybe a little less, but hopefully we'll have about 30 minutes for questions. Many of us who study the moon often use phrases, for instance, that the moon is the key to understanding the solar system, or it's the test bed to understanding the solar system. So I just was wondering from each of you if you could maybe share with us how the moon and the samples and the observations of the moon help us understand the solar system and our place in the solar system a little bit. Jack, maybe we can start with you on this one.
I'll go quickly because I mentioned this morning that once we had the samples back from Apollo 11, it was very clear the moon was a very old body. It recorded the history of the solar system. Yeah, at least the early part of that history very well, and that history was extraordinarily violent. And that included violence here on Earth, the violence created by very large impact basin formation. And if you've made quite a number of these on the moon, you made even more here on Earth. And so that characterized the early history of the Earth, probably the first 800 million years or so. And it was also a time in which complex organic molecules were getting organized. And one of the puzzles that I think we need to work out is how did that all work out? Why did we have that organization occurring at the same time that the Earth's environment was extremely violent? I think there's some potential hypotheses that need to be examined, but it is, I think, a very important part of why we went to the moon. In fact, I would characterize that as probably the most important knowledge about the Earth that we've gained from the moon, was this period of violence in its early history.
Not surprising, there's going to be some overlap with my answer with that Jack just gave. And I actually have a slide. I think I used it over a year and a half ago in the Webb Auditorium at NASA headquarters. I think captures this. It's the big ideas that I think came out of Apollo, and it's all generated by the samples. And they are the giant impact hypothesis for the origin of the Earth-Moon system, the lunar magma ocean hypothesis. You know, the moon was a differentiated planet, not an asteroid like Harold C. Urey thought. What was then called the lunar cataclysm hypothesis, we now think of as the inner solar system hypothesis, and we do debate the magnitude and duration of the late heavy bombardment, but certainly, as Jack said, there was an intense period of bombardment in the first billion years. That feeds into the impact origin of life hypothesis, this juxtaposition of the end of the basin forming epoch and the rise of life on planet Earth and potentially Mars. The magmatic epoch hypothesis, this new notion that the South Pole Lake and Basin may have caused an intense period of magmatism on the near side. And the most recent one, because we are still teasing things out of the samples, is the story of the moon's water and the origin of water in the Earth-Moon system. And that then has this fascinating twist into exploration, which I'll leave to Jen to talk about, but it's that we might actually utilize this for exploration.
Thanks for the segue, David. Yeah, so as something that Jake said in the introduction, you know, Apollo really started this renaissance in lunar science, and it's still going on. The story is still being untold, and we're still trying to figure out some of these mysteries. So as David mentioned, you know, we have samples back from Apollo that were very dry, right? There weren't flowing rivers on the moon, there weren't oceans of water, there's no sandstones, there's no shales, there's no limestones, none of those signatures of water. So when I grew up, we were told the moon is very dry, the moon is bone dry, thank you very much, moving on. But then it was about, you know, we got these samples, and then about 20 years ago, some more missions were being sent, Lunar Prospector was sent, people in this room worked on that. I'm looking at you, Rick Elphick. Right, and found these interesting signatures of hydrogen, particularly near the poles of the moon, and usually that can be a proxy for water. So why would there be enhanced hydrogen near the moon? And so this was very intriguing to NASA and to the science community, also for the exploration side. And so we've sent some follow-up missions. NASA Ames led a mission about a decade ago where we intentionally crashed the upper stage of a launch vehicle into a permanently shadowed region on the moon. So there are places near the poles of the moon, just because of the geometry and the way the sunlight's coming in near the poles, that have not seen sunlight for billions of years. Billions. Very, very cold, like 40 Kelvin, like colder than Pluto, extremely cold. So we call these cold traps because basically ices or volatiles, they get delivered there maybe by comets, maybe by asteroids, part of this bigger picture of where did this water come from in the inner solar system. And the water and ices can't get out, it's too cold, so they get cold trapped and they're stuck there. So we went and we impacted and kicked up a big plume of ice, dust, debris, and lo and behold, there was about 5.5% weight water there. Like there was water there in a usable amount for exploration. And so now NASA is taking the next steps to say, okay, we need to ground truth this water. We need to really figure out this story. Where is it? What form is it? How deep is it? How is it distributed? And then can we use it? Can we use it for sustained human exploration? So it's a really nice segue, these decades-long stories of lunar science that we're still working on today, and really at the intersection of both science and exploration. So these are some of the exciting things that are happening.
Yeah, to build off that, I think one of the really great things about Apollo is that it not only addressed these interesting science questions, but it enabled us to ask even more detailed and better science questions that we're still asking today. And so, for example, thinking about the whole water story, we didn't really understand how the moon formed, and then if it was such a catastrophic formation, what that meant for water being retained. And so when the Apollo samples came back and one of the professors at Brown, Alberto Saul, was able to actually find water in these volcanic glasses, that's actually one thing that's driven my own research and interest in being able to be part of this field. But I think overall what's really fascinating to think about is all the major questions that we're interested in, both the formation of the moon and the evolution of the moon, ties back to all of our big picture questions about Earth and the solar system as a whole. How did we get here? How did life form? How did our planet come to be? And I think that's why it's really important that we continue to explore the moon going forward.
All right, thanks very much for that. So with that, maybe I'll stop asking questions and go to the audience. Go ahead. Do we have a... Nope, here we go. If you go ahead and ask your question, I'll try to repeat it. That way we make sure we can hear it online, and then we'll go ahead to the...
Oh, thank you so much for the opportunity today. Jack, when you were prospecting on the lunar surface, did you sense that anything was not according to your training and your perception just by walking around, or did it all look like what you expected it to see from what evolved scientifically from the result of that mission?
So the question is whether or not when Jack was on the surface of the moon, he noticed anything that was not quite to the way he was trained to perceive the surface. Jack?
Just about everything that had a geological context to it was new. Our identifying resolution in the planning for the Apollo 17 mission was probably about 15 meters, something like that. So everything that we were seeing inside of that was new. And believe me, there was a lot that was new. Not only the discovery of the volcanic ashes at Shorty Crater, but it turns out we have at least 2 samples that I think came from the deep mantle of the upper mantle of the moon, say 400 or 500 kilometers down. That's based on textures that I was familiar with from my work in Norway. I didn't see them on the moon, but later on we've seen them here in the laboratory. Also, I think we found evidence in sampling both the North Massif and the South Massif regolith, excuse me, that there were pre-Mare pyroclastic eruptions. They were actually probably lithoclastic eruptions of debris that was entrained in early evolved volatiles prior to Mare melting and entrained out of the megaregolith of the crust of the moon. I think we have good evidence that that occurred. So you can see that each station tended to have something new and interesting, particularly in the context of the analysis of the samples once they were brought back to Earth. And that's very important to realize. It'll be some time, I think, before we have the analytical techniques on the moon that will enable us to do the kind of very detailed, deep dive research that can be done here on Earth. Someday that probably will happen. Someday we'll have settlements on the moon and laboratories that will be able to do that work in situ, so to speak. But for a while, and I think certainly in the next decade or so, that's going to have to be done with return samples. I might also mention that in the context of the water that has now pretty well been documented at the poles, with the Apollo 11 samples, we also documented that you can make water anywhere on the moon. Now you have to heat the regolith in order to get the hydrogen, the solar wind hydrogen, to react with the minerals that are there. But our estimates at the University of Wisconsin have been at about 600 or 700 degrees C, about a third of the hydrogen will come off as water. And so you have to play that into your thinking about long-term exploration of the moon and where you might put a settlement and what the cost trade-offs are and so forth. So that, I think, is a very important thing for people to remember and keep in the back of their mind, even though it looks like the target for 2024 is going to be in the areas of permanent shadow, namely at the South Pole.
Maybe an extension of that question. I know David and Jen, you've both worked with training folks in the field. How do you prepare people for the unknown when you're training in that regard?
Well, a
lot of field geological experience.
Yeah. So, yeah, Jack said it exactly right. And my number one training objective is to teach the astronauts how to observe and to communicate what they're observing to people in Flight Control Mission Ops Center. And they actually do that naturally very well. It's part of the selection process. I don't know if it is a particular element of the selection process, but astronauts by and large are brilliant people. If you don't know that, they are truly brilliant people. They're very good at observing things and very quickly making deductions that are correct. And as long as they can communicate in a language that the people in the flight control rooms can understand, you can make a huge amount of progress. Now, you have to introduce them to the right terrains. And for 2024, the thing that I tried to point out yesterday, it is nothing but an impact cratered terrain. And so we need to introduce them to impact cratering geology and how to work in that type of environment. And we did that during Apollo. We'll be able to do it again.
Jen?
Yeah, I think it's exactly what Jack said, field geology experience. You have to get out in the field and actually see the types of scientific features that you're looking for and how to interpret them. And so we've been lucky through several projects. We'll bring folks from the astronaut office, from NASA, from CSA, et cetera, into the field. Barbara Cohen led one of these to an impact structure up in northern Canada that hasn't been visited in decades, and now I know why, because it's really hard to get to. But so we do this, we bring the astronauts out, and one of the nice things, like David said, these are really smart people. And so what we've been doing is also not just having them do the field science, go out and do the field work, that's part of it, but then also being involved in the analysis afterwards. What happens to those samples when you bring them back into the lab? And so they have an appreciation and an understanding, because not every astronaut is a bona fide field geologist like Jack, right? And so they get really into it, and then they understand, okay, this is why we're doing this. These are the questions you're asking. These are the features you're looking for in the field, and this is why you need it, because when you take this back into the lab and you do your geochronology or your analysis, these are the features that you need. It's not always just the shiny rock over there that you want, but you need to be able to do the high grading, because you can't bring back every sample that you want. That's true from remote places on Earth. We often go to, we call analog features, places on Earth that have characteristics similar to where you'd be going on another planetary body. So you work within those same constraints and really teach them how to do that, have an appreciation for it, and have them be involved in the whole process while gaining that experience along the way.
Ariel, do you have any thoughts?
Well, I think what's interesting to think about is having this same conversation in another 50 years and having people talk about what that was like on Mars. And I think that we're going in that direction. So learning all these amazing lessons from people that have walked on the moon, people that are teaching people how to walk on the moon. And I think the vision is so grand that it's really, really incredible.
Great. Another question.
Hi, right here. Brad Bailey, Survey, soon to be headquarters. Soon to be. I got a couple questions, perhaps, revolving around technology. And so when you were on the moon, Jack, you had a rock hammer, and some of the most valuable samples came from the rake. Are there any current day technologies that you felt would have enabled you to take better samples or recognize different terrains in a more enlightened fashion? And the continuation to that question goes to the present and future lunar geologists on the panel. What new technologies do you think we should be investing in to help us do better planetary geology in total?
So the question was, what current technologies would have been helpful to have during Apollo, and what new technologies might we need as we look forward to activities on the lunar surface?
Very rapid general analysis of the composition of materials, and I mean very rapid. If it takes any time, then it's not an efficient use of the astronauts' time on the moon. Now that again assumes that we're not yet settled there and not have people who are working continuously as field geologists on the moon. We're talking about returning samples for use here on Earth, and as long as you're going to do that, any analytical work that you do on the surface is going to need to be something that's done very rapidly and very easily. Has been talk in the past of having robotic field assistants. Well, I have a feeling any robotic field assistant is going to be picked up and placed wherever the astronaut wants it to be, rather than depending on that robotic field assistant doing something that it's directed to do verbally. So I'm not a big fan of robotic field assistants. Now, if you give me a graduate student as a field assistant, then that's a little bit different. You have a little more authority, and they take some intelligence, hopefully, to the outcrop that you've directed them to. But analytical technology in the field needs to be extremely rapid and efficient and easily used to be, I think, useful. It's like an acid bottle here on Earth. The acid bottle is very easy to use. You immediately can tell dolomite from limestone from something else. That's the kind of thing you need on the moon, is an acid bottle kind of technology. Now, if you're talking about doing triage in a habitat, you're going to be there long enough to do that because you're going to collect too many samples to bring back, then you can do somewhat more leisurely analytical work in that laboratory. But out in the field, in a suit, trying to maximize the efficiency of your time away from the spacecraft or away from the habitat, I think the standard geological tools for collecting samples are going to, and of course you're taking your eyes and your brain with you. Those are very good analytical, semi-quantitative analytical tools, and have been used very good in the past during Apollo, and I think can be used very well in the future as well.
David, any thoughts?
Sure. So during Constellation, we tested some new technologies with 1, 3, 14, and 28-day long mission simulations. And we found there are some new technologies you want to utilize just routinely. We're going to drop the Newman. We're going to use digital photography. We'll have better data tracking. You saw a discussion of that both yesterday and today. But I would say, by and large, the most important capability that you can take to the moon is what we spoke about a moment ago, a well-trained astronaut. I've said this before, the best spectrometer you can ever fly is the eyes of a well-trained astronaut. They will observe things and make in real time important decisions, make adjustments to the traverse plan and collect the right samples. And I guess the other thing that I would say is that we want to be mindful that getting those samples back to Earth, we now understand how treasurable those are. We need to make sure that we have the lift capability to get those samples to the gateway so that we can bring them back to Earth. I worry that we are going to go to some interesting terrains. We're going to have sufficiently long traverses, that these very smart people, knowing what answers we want, are going to collect these samples that we desperately need to get back to Earth, and we're not going to be able to bring them back. And so, well-trained astronaut, sample return, mass capability.
Yeah, concur. We have this debate a lot. Can you just send a robot? Can it do what the human can do? And the answer is usually no. Usually you need to have the human there who can see, who can synthesize, who can take in a scene, who can make decisions. So for all these reasons, right, you need to send the people. And we're also looking at new technologies for what, especially for, like Jack was saying, rapid analysis in the field. So it's got to be quick. It can be quick and dirty, especially if you're high grading samples, because time is one of your most valuable resources. So we take instruments. We have a visible near-infrared spectrometer, taking that out. We have portable X-ray fluorescence spectrometers. We have portable laser-induced breakdown spectrometers. We take these out into the field and assess them to see which ones give you the best data and the quickest, so that you can make those decisions about which sites to look at, which samples to bring back, these very valuable samples when you can't bring everything. So looking at those analytical capabilities. And then also there's some really interesting new work going on, in the realm of advanced technologies like virtual reality and augmented reality. Heads-up displays. What's useful, and is anything useful? It's really cool, but now there's research going on now just starting to get into the quantitative aspects of that. So if you have a heads-up display that's got the terrain on it, can you overlay geologic maps so you can see what the different units are that you're looking at in real time, so you can make sampling decisions? You can have, you need to get from point A to point B. Maybe you deviated a little, so you need a new traverse path to get there. Well, you can have an AR, the computer works it out for you. Okay, what is the path that'll get you from A to B using the least amount of energy, taking into account the topography you need to traverse, your metabolic rate, your consumables in your suit, and it will map that out, and you just follow that through. So there's some really interesting new technologies that we're working on, a lot of groups are working on, and field testing these to see which ones are useful, which ones are not, and what capabilities need to be developed.
Yeah.
Yes, I agree with everything that's been said. And then the other aspect of helping with the rapid analysis is being able to allow for longer duration missions and more of a continued presence. So being able to invest in technologies and infrastructure that will allow us to continue to make these measurements in these studies, I also think is really important.
Great answers. Next question.
Yeah, this is directed to Jack Schmidt, but correct me if I'm wrong, but I heard you say you'd love for someone or appreciate someone asking you why were the specific science experiments chosen for Apollo 11, and I wanted to do a couple of derivatives of that. I gather it was 2 hours and 40 minutes time on the surface, or EVA. The time you were walking on the moon, was it a longer EVA, and did you have access to the lunar rover vehicle? But I guess I'll go back to the first part. Why were the specific experiments chosen for Apollo 11, and then on your own experiments?
Why were the experiment packages selected for Apollo 11 and also for Apollo 17?
As we led up to the Apollo 11 mission, you have to realize that things were moving very fast. And in the middle of 1968, the lunar module was in a bit of trouble. Its test program was not going well. We had to change out the ascent engine, which had not met tests well. And George Low had the idea that we ought to take Apollo 8 around the moon to keep the momentum up. He was familiar with that, having studied it as a member of the Space Task Group while he was at NASA headquarters well before Apollo was announced. And so he sold that. And in 4 months, depending on the success of Apollo 7, which was remarkably successful for a first flight of any spacecraft or aircraft, Apollo 8 went around the moon. And that bought us time, kept the momentum up. We learned a lot operationally. Mission Control got to work in deep space and so forth. But this problem with the lunar module and the weight of the lunar module and concern about having enough hover time was putting the original Apollo lunar surface experiment package, the ALSEP, in jeopardy. And I had done with the assistance of Don Lynn, had done a couple of deployments of that. Bill Anders and I had been at the PDR for the ALSEP. It was just not something that could be deployed in a reasonable amount of time. Unfortunately, the early specifications did not take that into account. Bendix was told, give us something to do by one of the astronauts who will remain nameless, and they did. In addition, it was 300 pounds, and that was worth 3 seconds of hover time. And so it began to be pretty apparent to me, at least, that we were not going to fly the ALSEP on Apollo 11. And at the time, there was Charlie Towns of MIT, Nobel Prize winner, was chairman of the President's Science Advisory Committee, and they had asked for a briefing by the astronauts of how NASA was going to conduct the first mission. And at the time that briefing was done, it was still considered to be a 2 EVA mission, and that the ALSEP would be deployed. But in the workup to that meeting, I was assigned to give the lunar surface portion of the briefing, and in the workup of the view graphs, I included on the last view graph an option for going with a smaller, lightweight experiment package. And I had already called Frank Press and Gene Simmons and the geophysicists of note of that time who had anything knowledge at all of the space program and the moon, and said, what do you think would be the best experiments if we never went back to the moon? That was the way I phrased the question. And unanimously they said a seismometer and a laser retroreflector. And that was what was on the view graph, and that's what Bob Gilruth said we were going to brief PSAC on. And once that was done, it was pretty clear that the ALSEP was not going to fly, but we would fly those 2 experiments along with Johannes Geiss's solar wind window shade, which didn't take much weight at all and didn't take much time to deploy. By the way, that's still about the best solar wind composition data we have today, was that solar wind.
Any other thoughts from the rest of the panel about that? No? Okay. Next, any other questions? Up in the back?
Yes.
Excuse me, Jake. One thing that I hope that story says is you've got to be flexible. These programs not only need to move quickly in order to keep the momentum up and make milestones, but you have to be flexible in the course of doing that. You can't be rigid, and the Apollo was not a rigid program. In spite of what some people may think, it was not a rigid program. It was because both at the launch vehicle level and at the spacecraft level, people were willing to not only take risks in management, but to move quickly when it was clear something had to be done.
Question?
Yeah, I have a question for Jack. So do you still recall what's the real smell on the lunar surface? Some people said it's like a gunpowder. Do you know what caused it, give you that smell? And have you smelled anything else similar on Earth as on the moon?
So the question is, do you recall the smell on the moon? And have you smelled anything like it here on Earth?
Well, you wouldn't want to smell what I smelled while I was outside the spacecraft, but inside the spacecraft, there was a unanimous conclusion among all the astronauts that I'm aware of that expressed an opinion is that lunar dust smells like spent gunpowder. And there's a good reason for that, I think. My hypothesis is that it's like activated charcoal. It takes a while, it takes some time before it starts to absorb the oxygen and moisture in the cabin atmosphere, and it is still activating your olfactory sensors as if it were activated charcoal. And eventually that smell goes away. But initially it's like spent gunpowder.
Any other questions? One up front. So this will probably be the last question. We've got about 8 minutes, so we'll take this one. And
one of the things that we all grew up using to study anything small is a microscope. And why are we so averse, or why have we not put a microscope on our spacecraft so far? Is there a reason?
So the question is that when we try to look at small things here on Earth, we use a microscope. So why do we not have microscopes on spacecraft, or did we not take them to the moon?
Go ahead.
Okay, so I'm a petrologist, so by definition, my life is centered around a microscope. But I'm also a field geologist, and it was never occurred to me to take a microscope with me into the field. There are two different aspects of conducting the science. And so when I'm traversing a terrain, whether it be volcanic or impact cratered, I am doing my field geology. I'm looking at things at one scale, trying to develop hypotheses and collect samples that I can return to the laboratory that will address the questions and test the hypotheses. And then once I get to the laboratory, yes, I want that tool, but that's not a tool that I need in the field. In fact, it would probably get in the way if it was with me in the field.
I did have a hand lens, but of course, it's a little hard to use a hand lens with a helmet, so I used it in the cabin. And in fact, between the first and second excursions, I did look at some of the basalt samples and revised my estimate of how much plagioclase was in those samples as a result. What had initially confused me on the surface, or caused a bias at least, were these little tiny impact craters we call zap pits. And they tended to over-accent the amount of plagioclase, because when they hit plagioclase, they shattered it, and it became much whiter than usual. And so my surface estimate was, as I recall, about 50% plagioclase, whereas with the hand lens I could see it was about 30%, and I think that held up in the preliminary examination. But a hand lens is very important, but it depends on where you can use it. And it may be you could engineer a low power hand lens like optics in the helmet, but I have a feeling NASA's never going to do that.
It's already happening, Jack. That's why I'm asking.
We got one, we'll have time for one more. We're going to go over here real quick if we've got the mic. Nope. Oh, sorry, Rick. I'm going to go with the next generation. I'm sorry, man.
Sorry, Rick. You're a has-been.
Sorry
I didn't
about
mean
that.
it, man. I still need you to work on those things.
So there's been a lot of talk of inspiration, and to me what I find inspiring is human experience. We've talked a lot about the science, but the human story is the value of sending people out into space is that we get the stories back. So my question is, what were your first thoughts when you stepped onto the moon? What was going through your mind? Did you have time to feel an emotion? Were you busy focusing on what was that like for you?
You want the real answer, or one that... The real answer is that my first thought was, don't fall. And the reason for that is my commander had somehow or another landed the front landing gear right next to a relatively smooth boulder. And when I came off, my boot slipped off that boulder because of these little tiny beads of what we now know were ash on the surface of that boulder. It was like little ball bearings. Well, fortunately, I was hanging on to the ladder at the same time, and I didn't fall, but that was my first thought, okay? Now, my second thought was how familiar everything looked, because I was working around a lunar module that I was very familiar with. I'd been through test after test, vacuum chamber, you name it, with this lunar module, and my vision right now was occupied by the Challenger, by the lunar module. And for the next several minutes, probably 5 or 10 minutes, the things we were doing were right there around the lunar module, including the deployment of the lunar rover, which happened fairly early on the first excursion. And it wasn't until one of my tasks was at the beginning of each excursion, each EVA, I went out at three corners, so to speak, of the lunar module and took a panorama. And that was the first time with a Hasselblad camera, that was the first time I had a chance to really see the Challenger in the context of this deep mountain valley we had landed in. The valley's deeper than the Grand Canyon. Mountains to the north were 5,000 feet high, mountains to the south 7,000 feet high, and really a magnificent place to be, brilliantly illuminated by a sun as bright as any New Mexico sun I had ever seen, and but also set against a blacker than black sky. That's probably the hardest thing to get used to when you're on the moon, at least for me, was the sky. The sun was bright, the sky was black. And then finally, you happen to look up high enough over the South Massif, over the 7,000-foot mountain, and there's the Earth, only 250,000 miles away. Hey, there's home. And anytime you want to see home, all you have to do is look over the South Massif. It was quite an experience, believe me.
So that about wraps it up. I have a couple quick thoughts at the end here. Listening to the conversation and discussion here, I think it's very clear how valuable the samples we brought back, the thoughts we brought back, the memories we brought back from the moon have been to the science community. So I think we need to thank the Hornet staff and the Hornet crew who were there that day 50 years ago for really setting the tone for analyses in the future. Jack?
I happened to just glance over here, and there's the shield of the U.S.S. Ticonderoga. That was the Apollo 17's recovery ship, and as you probably gathered listening to that outstanding panel we had earlier, the decision on what recovered a particular mission was pretty much ad hoc depending on what carrier was available. And there's a long history of why the Tycho was available, but it is really interesting, and I couldn't resist looking over that half fuselage there and to see the Tycho emblem up above it. Sorry, Jake.
So cheers also to the Tycho. Thanks to the Hornet. I also think we would be a little remiss not to remember a few other folks. When I first joined NASA, my first day, I was told very clearly one of my jobs was to learn as much as I could from those who were still remaining from Apollo. I've been at NASA for 13 years, and there aren't too many of those folks still working for NASA, and many of them are not with us at all anymore. And I can only imagine from Jack's perspective what that's like. So I think we should also at least acknowledge the memories and thoughts and voices that we could not invite to these activities over the last week, because there are some important ones. So
absent friends.
So we'll bring Greg back up. I just wanted to say it's been an honor for me to be up here with this panel of some of the best scientists we have working on lunar science. So thank you all very much.
Thank you, Jake.
Thanks, Jake. That was great. Thanks, Jake. Awesome. Thanks, Dan. Yeah. Thanks very much, Jake, and thanks to all of our panelists. I think that was just fantastic. I learned a lot myself, and I hope you did as well. So our next event is a little bit of a surprise. It's not on the agenda, but I think you're going to enjoy it. Let me start off by asking Ben to come up here. And Mike and Laura, would you mind coming up on stage as well? So how many here have seen the movie Apollo 11? Yeah, I mean, right? This is the right audience for that. Absolutely stunning. We have here Ben Feist, who was one of the producers of this movie, and who, And in the production of this movie, came across a lot of very interesting material. And so he's going to tell you about something very special that he found. So Ben, please.
Thanks very much. Hi, everybody. It's a great honor to be standing here on behalf of the rest of the film team that made Apollo 11. As part of the effort for that film, there was a huge amount of archival research conducted, and part of that was not only the stunning footage that will be later donated to the Hornet Museum, but we also came across thousands of hours of audio recorded in mission control. And this audio has not been heard for 50 years, and a lot of it was used to bring sound back to the silent footage that was filmed during Apollo for that film. As part of that, there are 4 channels of audio that was about recovery operations that centered around the U.S.S. Hornet. And I have restored that audio, and there's 1,000 hours of it on this tiny little flash drive, much smaller than the original tapes that were in the National Archives that we found. And today I'm donating this to the Hornet Museum as something that has not been heard. There's family calls that were made home by the family members. There was lots of, obviously, coordination for recovery and discussions around quarantine and things that have never been heard. And it's like a window being opened into the past. I believe we have a short clip that we could play right now of some of that audio.
Houston Recovery, Hornet Recovery, I read you loud and clear. Have you confirmed command module, service module separation? Over.
Roger, Hornet Recovery. We confirmed that approximately 10 minutes ago. Passed it out to Mel. Over.
Roger, understand. I'm up on the ship's bridge right now. I just finished briefing the president, and he's out on the port wing of the flag bridge immediately below me here. It looks like it's pretty well clobbered up out here. I doubt very much if we get to see anything. Our sea state and winds are not bad. It's simply the high cloud cover, and I doubt that we're going to get to see anything. Over.
Roger, understand.
So there's a lot more of that. If you're interested in hearing it yourself, you can hear it at a website called apolloinrealtime.org, where it's all locked to mission time. Thank you.
On behalf of the Board of Trustees and the staff, Laura, who runs the museum, basically. She keeps me on time. She's our curator, makes sure all these collections go through. This will be put to very good use, and we're very honored to accept this. And it's been a great pleasure for us, for me, the kid who used to watch the launches at ODARC 30, my dad would get me to watch them. It's been a great treat to see Harrison Schmidt and other people here. So thanks for making us part of your day. We really enjoyed it. Thank you.